Hello everyone. Today I'd like to talk to you about my research with machine learning image classification techniques and how we can utilize machine learning to further our understanding of the Martian terrain. I'll start by giving you some brief background knowledge about the Curiosity rover and its various engineering capabilities, as well as the project's goal and relevance towards machine learning image classification and Mars research. Next, I'll describe the data used in this research, where it comes from, the type of data it is, and the data collection methods used. I'll also give an overview of the different terrain classes that Curiosity encounters on its journey. Additionally, I'll give a brief description of the dynamic albedo of Neutron's instrument and how it ties in with the goal and relevance of this research. Following this, I'll discuss some of the exploratory data analysis methods as well as the overall model architecture. Finally, I'll explore the possibilities in the future that this research paves the way for. In November of 2011, the Mars Science Laboratory mission sent Curiosity, a robotic probe, on a journey to Mars in search for evidence of water. Curiosity was equipped with 17 different cameras and various measurement tools, all for studying the Martian terrain. The dynamic albedo of Neutron's instrument is used to measure the water content of the subsurface, and the rear hazard cameras provide a clear view of the area being measured. With this in mind, the project goal is as such: to develop machine learning classification models to predict the terrain types behind the rover. This helps with processing neutron data, which is used to quantify hydrogen, water, in the Mars subsurface. The Neutron instrument is influenced by the presence of sand and soils at the rear of the rover. The data comes from a public repository of images sent from Curiosity and is provided by the United States Geological Survey. Images are organized into subfolders based off of the sol, or Martian day, the image is taken on. The image file names consist of a string of characters that details the image metadata, including the camera used, image resolution, and corrections applied to the image. The file names were decoded using the SIS documentation provided in the online repository, which helped to narrow down the most relevant files. To collect the data, I designed a script in Python to utilize HTML-based scraping on the USGS online repository to download files with the relevant file naming conventions. The downloaded images were placed in a directory structure that mimics that of the online repository. I also constructed a data frame that contains the image metadata and labeling attributes, which will help in the model building process. Image data was collected for the first 1,500 sols of Curiosity's voyage, totaling over 10,000 images to be used for training and testing. The 4 types of image classes the models will be trained on are bedrock, sand, a sand-soil mixture, and dusty bedrock. The dynamic albedo of Neutron's instrument, or DAN for short, is a tool used for locating hydrogen atoms along the subsurface within a certain proximity of the rover. Located at the aft of the rover, the DAN instrument is extremely useful for finding signs of water on Mars. One indicator of the presence of water is the calcium sulfite deposits found in certain regions of Mars believed to have once contained large bodies of water. By flagging images that contain these bright-toned veins, we can utilize the instruments on Curiosity much more effectively for research and observational purposes. The exploratory data analysis of this project will focus on comparing the performances of the models. Using different classification models, I can compare the performance metrics to find the most effective model. Additionally, images that have a less clear label will be flagged with a low confidence level attribute, which we can feed into the models to introduce variation and observe how it responds to those variables. The first 2 stages of the model building process are the data acquisition and development stages, which were discussed in the previous sections. The third stage in the process involves data cleaning and pre-processing, which includes cropping images, removal of bad images, data conditioning, labeling, and fold design. The last stage of the process is the model development stage. Here, I will perform cross-validation on the dataset to help create a more robust model. As for the model itself, I will be conducting a model trade study, which will include decision trees, k-nearest neighbor, and support vector machines classifier. After the models have run, a comparison will be done of their performance metrics to find the machine learning model best suited for the task. Overall, this research will open the door for many other machine learning applications for planetary research. An effective classification model of this caliber could be implemented on not only other Curiosity cameras, but other rovers as well. Developing powerful machine learning models for rovers will come to be a crucial component in the coming years. And as our curiosity expands, so too will we need to ensure that we are utilizing the capabilities of robotics probes to their fullest extent.